Good evening all. Welcome to live session 9 of Computational Fluid Dynamics for Incompressible Flows. Quickly going through the contents, we started out with the governing equations for fluid mechanics, and then we classified different kinds of PDEs, elliptic, parabolic, hyperbolic, depending on how information propagates through the domain. And then we identified a method called finite difference method, and we used that to solve each of these PDEs. And then we established something called stability convergence criteria, wherein we describe how or when these particular schemes are actually lead to a stable solution. Following that, we analyze how to how to get the stability criteria using von Neumann analysis method. After that, we discussed, okay, we'll move on to Navier-Stokes equation, but for a simplified case using vorticity stream function formulation, wherein we use the assumptions that the flow is 2D, and with the 2D assumption, we were able to simplify the problem. And then we eliminated, we converted the problem from u comma v comma like from the three variable u with p primitive variables to stream function and vorticity variables. So from three variables to two variable, and then we solved that in the last week. This week we will discuss something called marker and cell algorithm, which is used to solve unsteady Navier-Stokes equations. To summarize, we'll start with something called staggered grid. So up until now, even in the last week when we discussed what is the stream function formulation, we were using say if this is a grid. So let's take a 1D domain so that we can understand it easy, and then we will extend it to 2D. So for a 1D problem, what we were doing before is, let's say these are the points. So I'll discretize this domain into some number of grid points. Right. So we discretize the domain into certain number of grid points, and then but all the velocity variables, like previously when we were using vorticity stream function formulation, the omega and psi values are stored at these grid points. So if you were to extend the same analysis to u comma v comma p, like the three primitive variables that we will be solving in case of 2D problems, so we will encounter some problem called checker coding. That is, and to eliminate that, we use something called staggered grid. That is something that we'll discuss first, and then we will use that extend from there to how to discretize Navier-Stokes equations for 1D and then 2D, and then you can extend from there to 3D or other problems. And then some previous year assignment questions we'll discuss. Following that, we'll see how to code this thing for 1D and 2D flows. So why do we need a staggered grid? So let's start with a 1D example. So if I take my Navier-Stokes equations in 1D, so for continuity, I'll be having just del u del x equals to 0. And for momentum, I have only x momentum equation, which will give me del u del t plus u del u del x. Something of this kind. So if you were to discretize this on a 1D grid, so this is my grid domain, this is my first, and so on. So this is my 1D grid that I've discretized my domain. So now the first one for the continuity equation, if I were to discretize del u del x at the ith grid point, and let's say I'll use the central difference scheme, so that will give me ui plus 1 minus ui minus 1 by 2 delta x equals to 0. If I solve this, so this essentially gives me ui plus 1 is ui minus 1. Or in other words, you can start with u1 is u3 is u5, like every alternate things will be equal to each other, and so on. The other way around. Similarly, we'll have for u2 and so on. But there is no constraint that says that relates between these two quantities. So depending on the boundary conditions, let's say the u1 is specified as some u, and let's say here we have a different boundary condition that will enforce the values of what these velocities are going to be. Now, if you do the same discretization for this, let's say we'll start with study case, so it will be little easy. So for a study flow, u times del u del x at ith discretization, so I'm doing at ith point, it will be ui times del u del x Similarly for del P del X will be Pi plus 1, and del square U del X square will be Ui plus 1 minus. So you know this term is going to be 0 because from the equation Ui plus 1 equals to Ui minus 1, and we'll be left with these terms again. So here again Ui plus 1 is equals to Ui minus 1, so we'll be left out with. So in typical problems, if you encounter a problem where the values of diffusion is very less or your viscosity is very less, then in those problems this thing will get dominated and you will end up having Pi plus 1 and Pi minus 1 to be equal to each other. And then this is where the problem starts. So if this is the case, then we'll again end up with the same set of equations that P1 is P3 is P5 is so on. Similarly for the alternate set of equations. So there is nothing that relates with between P1 and P2. So that is what we will call that. This is what we are essentially calling. In reality, in real fluids, what we have is this pressure and velocity are dependent on each other. Like any changes from pressure will actually affect the local velocity field. Eventually, from there it gets propagated throughout the domain. If it is if the problem is kind of for incompressible flows, it is elliptic, so it will eventually get dominated throughout the domain. But the problem here we'll be having here is we are getting two sets of solutions and both are not kind of related with each other, and this is happening essentially because of the way we are discretizing. So instead of using a central difference, if I were to use a different one here, let's say I'll use so the other scheme that was proposed is, so the main challenge here, as I said here, is we have a derivative of this. Here we have ui plus 1, ui minus 1. Here we have pi plus 1, pi minus 1. So we are only considering the derivative such a way that the current cell is always ignored. So and both u and p are aligning in the same direction. So what we will do now is instead we will use a different set of cells. We will use some marker cells in between, or let me put a new grid, the same domain, but now we will define the center points. If these are my previous nodes, so this is my 1, 2, 3, or the ones that I was using before is the same way. This is my 1, 2, 3. So instead of defining it exactly matching with the cell domain boundaries, we will take the grid coordinates at half distance away from it, and then we will use other set of coordinates, let's say half, 3 by 2, 5 by 2, and so on. So at any given point, if this is my ith cell, I'll have I plus half, I minus half, and similarly I have I minus 1, I plus 1, and so on. So what we are trying to do now is instead of discretizing the same equations or at the same grid point, we will discretize the equations at two different grid points. So let's say we start with the momentum equation. Let me just ignore the diffusion for now. Let's say this is the equation. I'll discretize this at on the half grids. So I'll only discretize this at the circular coordinates. Wherever I mark this circle, at this point I'll discretize all these points. I'll discretize the momentum equation, and all the cross points I will discretize my continuity equation. So let's see what happens if I do that. So we start with the momentum equation. So I'm discretizing it I plus half. So let's say this is the half coordinate. So at this point, I can write this as ui plus half times del u del x for this point. Again, I'll use a central difference scheme. So I have here I plus 3 by 2 minus. So we are doing central difference around this point. So I plus 3 by 2 minus I minus half by 2 delta x is minus 1 by rho times del P del X. At this point del P del X, I can write it as Pi plus 1 minus Pi by delta X. So this is again, we are doing a central differencing, so this is second order accurate. But you can see the difference here, that in this formulation, Pi is actually coming into picture. Now let us also do discretization for the continuity equation. So del U del X, this I'll be doing at ith grid point. So at this point, if I'm doing del U del X, so that's I have central differencing at ith point will give me I plus half minus I minus half. So what this does is this will kind of force I plus half equals to I minus half and so on. So every point will be eventually made equal to 0. So if the initial value is u equals to 0 throughout, so this solution of the continuity equation will ensure that each and every point, that is these circles, are going to be 0. The velocity at all these circles is going to be 0. I think I gave the wrong representation here. Sir, cross marks are my I, and the circles are I plus half, I minus half, and so on. Yeah. So this will give me I plus half equals to u, I minus half, and so on, all of them being equal to each other. So each of these being equal to each other will essentially mean I plus 3 by 2 and I minus half will also be equal to each other. So that will essentially eventually boil down to saying Pi plus 1 equals to Pi. And if this is true, then all the pressures will also be 0. So this was not possible before because of we have two different, when we wrote the equations previously, we were having P1 equal to P3 equal to, so the alternate, the values at the alternate coordinates are being equal to each other. Similarly, for all the even will be equal to each other and all the odd will be equal to each other, and there is no relation between these even and odd quantities. That was the problem before, and that is what we call the decoupling. So if what we did now is we are doing discretization of continuity at different grid points and the momentum equation on other grid points, that will essentially ensure that at these grid points the velocities will all be equal to each other, and using that in the momentum equation will essentially give pressure will also be equal to each other. So this will essentially give me P1 equals to P2 equals to so on, and this will give me U half equals to U3 by 2, U5 by 2, and so on. So this way we can avoid the checkerboarding pattern, which essentially means that odd even thing is not happening here. All of the quantities will be equal to each other under this particular case when U is 0, and this is called pressure velocity coupling, is what we are introducing by staggering the grid. So extending the same thing to 2D is also the similar, where the idea is you have the same grid points. Let's say we have a 2D domain. So these are my actual boundaries. So now what we have to do is similar to this. So in the 1D grid, we started with, let's say this is the arbitrary 1D thing that I have here. So first we define the cell centers, and it is these cell centers where pressure is being stored. And then I have phase centers. These are my phase centers, which are essentially this. Let's have added one more cell also here. So these dots are my phase centers. At these phase centers, we will store the velocity. So this is along the one line along x direction. Similarly, I can draw a line along y direction. Let's say if I were to draw something like this, and I will do the same thing. So where I'll have cell centers. So these are my cell centers, and accordingly, that is where the pressure is being stored, and I'll have phase centers. Where velocity is being stored. So along the x direction, these are the points where I'll be storing u. These are the points where I'll be storing pressure, and along this vertical direction, these are the points where I'll be storing v. So just to kind of make it easy when we write code. So if I'm denoting my coordinate system with I comma j. So this is where my pressure will be stored. Then velocity will be stored on I plus half comma j. So essentially I plus half, I minus half, all those half coordinates for along the I direction will have u, and similarly for all the j half coordinates will have v. Maybe instead of 1 by 2, so I can write it in this way, and be more general. I can write it as I plus some n by 2 comma j and I comma j plus n by 2, where n is some integer between minus depending on whatever your domain size is. So what we are doing now is these half coordinates, like when we write an array matrix, so when we write this as a matrix, so you can see here that I have 1 to n, let's say eventually it stops at n. If I have n nodes for pressure, then I will end up having, for every node I'll be having one phase center, and this will be common between 1 and 2. So for 1 and 2 I'll have 1, 2, 3 phases. For 3 nodes together I'll have 4 phases. So on for n nodes I'll be having n plus 1 phase centers. So my P, if it is a dimension of n cross n, then my U is going to have dimension n plus 1. Along x direction it will be plus 1. Y direction it will be the same, because j is the same coordinate as this. So there won't be any deviation along the y direction. V will be exactly the other way around. So for V we have I is the same index running from 1 to n, and along j we have this half coordinate, so we'll have n plus 1 nodes. This is how I define initialize my matrices, and then I'll have to go ahead and solve them. How do we solve them is something we'll see now. So let's again start with the 1D case to see how we solve these equations. So my governing equations are del u del x equals to 0, minus 1 by rho del p del x, and my grid is same as before. I plus half, I minus half. Just write all the half coordinates on the top, and so on. So the idea in math is first we start with the momentum equation. We will discretize the momentum on half cells. So in general, we will discretize on let's say the I plus half cell. This cell is where we will start discretizing the momentum equation. So for the time coordinate, we will use the explicit time step at I plus half coordinate. So in the explicit formation, you have ui plus half n plus 1 minus ui plus half n divided by delta t plus whatever we have before. So for u, this is where our whatever we learned in the hyperbolic equations come into picture. So how do I use what will be the quantity I'll be using for u del x? So here again we have different difference schemes, the upwind, central differencing that we discussed before. So let's say if I am to use the central differencing scheme. So in central differencing scheme, u will be replaced with ui times del u del x at this particular point will be, if I am using central difference, that will have ui plus 3 by 2 minus ui minus half by 2 delta x. This is with central differencing. Say if I were to use the upwind scheme or something else, then this will be replaced with a different one. So if I'm using upwind differencing, then if the velocity at this particular point is positive, then I have to use information from the previous cells. So the derivative at this particular cell from the previous value should have ui plus half minus ui minus half by delta x. Upwind is only first order accurate. Central differencing is second order accurate. This is if ui is positive. If ui is negative, then we'll have it in the other way. So this will be at this point if it is negative. So we have to take the other coordinate ui plus 3 by 2 minus ui plus half by delta x. This is for upline. And any other scheme that we discussed in hyperbolic equations, accordingly you'll have to change this discretization here. So that will be with respect to this. But the problem, as you see here, is I'm writing ui, but as I said, for staggered grid we store velocity only on the half cells, so we do not actually have the velocity of ui with us directly. So what we do now is we'll estimate ui as I plus half plus I minus half by 2. So we'll take the average of the neighboring nodes, so I plus half and I minus half by 2. Again, this is, we'll substitute back here, equals to minus 1 by rho. Del p del x, again we'll use central differencing. So we are doing discretization at this particular point. So del p del x is basically pi plus 1 minus pi. Again, we are using explicit formulation here, so it will be all. Here we use the n plus 1 by delta x, I plus there is difference 1 plus this is straightforward. The diffusion is straightforward. You have ui plus 3 by 2 minus ui plus half plus ui minus half by delta x square. So as you can see here, we have two unknown variables. One is all these values of velocity at n plus 1, which we do not know, and the pressure also we do not know at n plus 1 coordinates. So we essentially have two unknowns that we need to solve for, but this is only one equation. So what is done in MAC algorithm is we try to split this into two different steps where we actually haven't used the continuity equation yet. So that should additionally give us one more equation, and solving this along this momentum along with continuity should help us solve ui n plus 1 and pi n plus 1. So the idea now is we, instead of solving for ui n plus 1 directly, so we'll use something called a predictor step, where instead of directly getting the value of ui n plus 1, we will start with something u tilde, where u tilde is the quantity that we will be predicting from this equation with Pn values, with the pressure values from the previous time step. So instead of solving this equation directly, what we will do now is, so everything else remains the same except for this quantity here. So we'll use the previous time step, and accordingly this will also change. So this will be my u tilde. So this is the first equation where we from this equation all we have to, all the values are known to us. The previous the at the previous time step we know the pressure and velocity, so we can substitute that into this equation and estimate the value of velocity, which is the predictor step. The next step is, we know that this velocity is not correct, so we have to come up with improved velocity, because this velocity uses the previous time steps pressure, so this is obviously not equal to the ui plus 1 that we are looking for. So we need to solve for a different equation to get the value of ui n plus 1. So that is where there are different ways to do that. So the one that is used in MAC is we subtract this equation, subtract 1 from 2, and define the pressure correction as something as Pn plus 1 minus Pn. And from this we can write a new equation which says un plus 1 So the advection and diffusion terms will cancel each other. So all that we are left with is the difference between these pressures, which gets converted into the pressure correction P prime, and the difference between these two quantities. And from this equation, we can write the expression for un plus 1 as whatever is the velocity obtained from the correction step, from the prediction step, minus rho delta x times P prime I plus 1 minus P prime I. I have calculated u tilde, but I do not know the value of p prime yet. So I have to somehow solve for this equation. That is where we will use the continuity equation. So if I were to write this just to kind of simplify to make it a little more intuitive. So what we are trying to do here is we are trying to estimate un plus 1 as u tilde minus this. You can write this as essentially something like del p del x. Here we are only dealing with 1D problem, so I can write this as dx. So this is what we are having, and what we are trying to do now is enforce continuity equation on this. So what we will do is du dx, or essentially del u del x at n plus 1 step is del u tilde by del x minus delta t by rho times d square p dx square. So this is where we will enforce the continuity equation. So we will say that we need this quantity to be equals to 0. From continuity, we know that this quantity has to be 0. So that will give us a new equation, which is d square p prime, sorry, d square p prime by dx square is rho by delta t times del u tilde by del x. If I write this in the discretized form, we can use again central differencing for this, so that will give me p prime I plus 1 minus 2 p prime I plus p prime I minus 1 by delta x square is rho by delta t times del u tilde del x. I can write it as whatever I have before. U tilde of, yeah, again for continuity, we are doing this on this point. This is my continuity and this is my momentum. Continuity we are discretizing at the ith point. That is the main idea of staggered grid. For continuity, we will discretize at cell centers, which is this I 1, 2, 3, and I so on. And for momentum, we will discretize at this half ones, I plus half, I minus half, etc. So for continuity, we are doing at the ith cell. So del u del x at ith cell will be I plus half minus I minus half by delta x. So this is basically Poisson equation, which we already learned. How to solve this Poisson equation is something that we already discussed before. You can use Gauss-Seidel method with over relaxation, under relaxation, whatever, depending on the problem. Here, say under relaxation or over relaxation, and you can solve this thing. Or you can use the direct method that we discussed. So basically, this will give you a matrix, something of this sort, equal to some source term B, and you can use any of that. So this is essentially, it will result in a tridiagonal matrix, and all you have to do is use TDMA algorithm that we discussed before, and then solve for the value of P prime, or use Jacobi method, whichever method that we discussed before. And what will be the boundary conditions for this equation is we have P prime is basically the correction that we are applying for. So if you have Dirichlet boundary conditions for pressure, there are no corrections that needs to be applied on the boundary, so P prime will be 0 there. And with that, you will be able to solve for P prime. Or the other thing that was discussed in the lecture is, instead of, we can simplify this further by saying that the correction from the neighboring, like we know that this u tilde is basically not the previous velocity or not the actual velocity. So this is some kind of a provisional or whatever you predicted from the previous step. So instead of going to solve a full Poisson equation, which is going to take a lot of time, what we'll do is assume that the contribution from the neighboring cells is negligible compared to the main cell. So that will simplify the problem further, and then you simply write this as pi prime is minus. So essentially, I'm making these two terms as 0, or assuming these terms as 0. So that will reduce my problem by, we are going to have delta x by t, delta t by rho delta x. Again, since we are doing this approximation, which will essentially mean that it will not, like if I take this directly, then it will either over or understood. So I have to do some kind of relaxation. So the two I have observed into this omega. So I'll have to use some omega that is kind of less than 1. So I'll be doing this under relaxation. So whatever correction I'm doing is not too high so that it will blow up or something. So what we'll do is essentially is, we know the value of u tilde that we calculated from the previous step. So this is a u tilde I got. So you already know all these values. So from this we'll get a u tilde. And from that u tilde, you can calculate this pi prime, which is again an estimate that we are making. Ideally, we want this equation to be solved, but what we are doing is we are assuming, we are kind of simplifying that into this equation. So what we'll do now is we'll have an estimate of pi prime, and with this pi prime estimate, we'll proceed further till into this equation. So what we'll be doing now is, okay, you got a pi prime, which is again a provisional velocity, which is not, sorry, which is a provisional pressure. It is not a final correction pressure that we'll be going to get. If you solve this directly, then you will directly get that. Because we are not doing that directly, because we made an assumption here, this is kind of an estimate. So the velocity that I'm going to get here is not the final velocity. Instead, it is again another provisional velocity. So this is what we call the correction step. So what we will do now is use this p prime in this equation and update the value of u theta to get a new value of velocity, and then again proceed to do the same as follows. So use that again here, and then you update p prime, and you keep doing this till we have the value of this to be less than whatever tolerance you are having. Once this is done, we'll have like after this, once this criteria is satisfied, all we'll be having is we now have a u tilde, which is basically an a p prime, from which we can calculate u I plus half n plus 1, and we can also calculate the p n plus 1 values. P n plus 1 is basically p n plus whatever p prime I have calculated after this as converged, after this entire loop has converged. So I'll be having the velocity p n plus 1 and u n plus 1 and p n plus 1 and for the next time step. And this I have to march in time, just like what we did in the parabolic equations, like use an explicit or cranking constant, whatever scheme we are using. Depending on that, you march in time. This is how we approach the MAC algorithm. So before going to problems, maybe we'll see how to implement this in code, then it will be a little clear, and then we'll move on to 2D also. So the main steps are, the first step is, to summarize, the first step is we need to do the prediction step, where we need to predict the next velocity. The next step is the pressure correction. We need to compute the pressure correction, estimate this thing, and then we have to correct the values of u. And we have to do this till this particular convergence is reached. Once the convergence is reached, we can march the time step one by one. So implementing this thing here is, for the prediction velocity, we will be taking, okay, let me just define the variables first. So u tilde is whatever I just showed. This will be the provisional velocity. U and p are the velocities that we have. Dx, dt are, dx and dt are the same as applies. So what we are doing now is for j equals to 2 to n. So I should have different coordinates also. So these are my I coordinates, and for the half cells, I'm denoting with j coordinates. So the coordinates will look something like this. So if I is running from 1, 2, and so on, there will be my other set of coordinates which are at the phase centers. So these are my I coordinates, and these phase centers are my j coordinates. So j equals to 1, 2, 3, and so on. So I ends at n and j ends at n plus 1. So what we are doing is j equals to 2 to n. So for all the interior cells, if you take at any coordinate j, so if this is my ith one, the corresponding j. So for 1 we have j plus 1 here. So for this I, the way we are discretizing now is, we discretize the continuity equation here, and we discretize the momentum equation here. So j is basically I minus 1. So that is what I have written. I have written it in the other way. Okay, equal to j minus 1. So first term is the advection term. We are using central differencing. So it is u of j plus del u del x is j plus 1 minus j minus 1 by 2 delta x. Similarly for the diffusion, again we use central differencing. So this is j plus 1 minus 2 uj plus uj minus 1 by delta x square. Pressure, again it is also a central differencing scheme. What second order accurate, we are expanding this around this point. So around I plus 2 if I am discretizing, so it will have east minus west by 2 delta x. that is I plus 1 minus pi, pi plus 1 minus pi by delta x. And then from this we'll correct the velocity. U tilde is u plus delta t times pressure term plus diffusion minus advection. So this will give me the u tilde, and this we are only doing at the internal cells, so we have to update the boundary conditions. So this function does that update. I've not written what this function is. This will, because this will change from problem to problem. So once we calculated the velocity, then predicted the velocity, the next step is to compute p prime. So p prime is this equation. Omega is the relaxation factor times del u del x by delta t, rho delta, delta t by rho. So I've assumed rho to be 1. So this is minus omega naught times u tilde, this is the del u del x term, u tilde j minus u tilde j minus 1 by del x. And then you have 2 delta t here. So I've given 2 here, but accordingly this will get adjusted into the omega naught value that we have. So this will compute the p prime. Once I have p prime and I have the predicted velocity, now I have to correct the velocity. So velocity correction is u n plus 1 is u tilde minus delta t times del p del x, del p prime by del x. So where del p prime del x is p prime I plus 1 minus p prime I. So this will give me a corrected velocity. Again, this velocity we are only doing it the internal cells, so now we have to apply the boundary conditions. Similarly, for pressure correction is p n plus 1 is p plus p prime. So this plus equal to is an operator here. This is just to compute the mass imbalance. Mass imbalance is this term that I have shown here, del dot G. This is basically what we call mass imbalance. What it calculates is it just checks whether the divergence free condition is getting satisfied or not. So it will calculate the values of divergence throughout. I could have put dx and written it in each. The next step is the max step. So what we do here is this iteration that I was showing before. The first step is you compute p prime, and then you correct your velocities, correct the pressures, calculate the mass imbalance, check whether the mass imbalance is within the tolerance or not. If it is not within the tolerance, you again do the same thing. This keeps repeating. And this is the final run where you do the time marching from 1 to n steps, where you start with the previous velocity and then you keep updating your time step. Take a simple problem also, or we'll look at the problem later. But are there any questions in this? There are no questions. So the only difference from this when we move to 2D is in the grid we have a little more complexity. As in, let's say if this is my domain, these are my actual domain boundaries. Let's say these are my cells. So I'll have the cell centers. Cell centers will have the pressure, and now I have to define the phase centers. So along x direction, these are my phase centers. This is where my u velocity will be stored. Similarly on the boundaries, you can see that we'll have only 1, 2, 3, 4, 5, 6, 7, 6 of these, and we do not have anything on this boundary here. And then we have the other vertical velocity, which will be on the vertical faces. And that will only extend along this. So now if we count the number of cells, so this is basically a grid of 5 cells along x direction and 6 cells along the y direction. So this will be the size of my pressure matrix. Now for the u, you can see along the x direction we have and along y direction we'll be having 6. This is for u, and similarly for v, Along x direction we have 5, along y direction we have 7. So this will be the dimensions of the matrix for this particular grid. Now everything else remains the same, just that the way we write equations, like we just have one more additional term here. So let's only do for x momentum. I think the method is straightforward, just for sake of completeness. Let's take the x momentum equation. So I have del u del t, u del u del x, v del u del y. So just like before, we have three equations here. So we have continuity, which we will discretize on I comma j cell, I comma j nodes. We have x momentum, which we will discretize on I plus half comma j. Essentially, when I meant I plus half, all the half integer ones, so I minus half, I plus half, all these ones, all these horizontal faces that I have drawn. And for y momentum, we will discretize on, we'll keep I constant and we'll discretize on j plus half. Or maybe I can write j plus n by 2 or I plus n, something like that, where n is some index that will run throughout the grid. So if you are doing this discretization, so this is my I comma j cell. So for the first x momentum equation, I should be doing on I plus n by 2 comma j. So that is this cell. So if I'm doing across this, so this is I comma j, this will be my I plus half comma j. So when I discretize at this point, so del u del t, so it will be 1 by term. So the unsteady term will be basically ui plus half, whatever we have before, but j coordinate should remain the same, minus ui plus half comma j by delta t. This will be the unsteady term. Now the advection component, we are discretizing at this point, so we'll use u comma v at that point. So it will be u I plus half comma j. I'm not writing any superscript. If I'm not writing any superscript, assume that it is at the end. So without any superscript, just take that it's at the current time step only. So ui plus half j times del u del x. So del u del x at this using central difference will be this minus the previous one. So that is u I plus 3 by 2 along the same direction. So we are keeping j constant as we are doing the central difference in here. U minus half comma j by 2 delta x. Plus similarly for v also we are discretizing at the same point. This should be v I plus half. Now we have to do del u del y. So del u del y should do the central differencing along critical direction. So I have to use a different color. So at this point, so these are my velocities. That should give me along y direction, I should be constant. So ui plus half. So this is j. So this will be j plus 1. So these are my j plus half, j plus 3 by 2 and so on. So this is in line with the cell center. So this will be j plus 1 minus at the bottom one, it will be the same I value, but it will be j minus 1 by 2 delta y. The only problem in this is we do not know the value of this because v is only stored at I comma j plus n by 2. This is something that we do not have. So just like before when we were doing in case of continuity, we essentially assume the value of here to be average of the neighboring cells. So we use the same trick here. So vi plus half is basically the value of v at this point, which we do not have. So what we will do is we will take an average of the neighboring points. So velocity at this point, all the neighboring points, I use different color. This blue. Okay. This is my v. So these v values we will be using to get the average vi plus by 2 half. Vi plus half comma j. I should basically write it in a form that it will only use I comma j plus n by 2. So all I will be doing is, so at this particular point we have, let's say this one, which is vi plus 1, j plus half plus vi plus 1, j minus half. So these two will Both are possible because this is along integer index and this is the half integer indices, which where velocity is getting stored. Similarly, on the other directions, which will be vi j plus half and vi j minus half. Just arithmetic mean of all the four. This vi plus half comma j, we can use it here, and then we can solve our advection component. Now, similarly for the pressure term, it's straightforward, just as like before. So for pressure, we have del P del X. We are doing discretization at this particular point, so del P del X should have these 2 points. So pressure term is basically this minus this, which is minus Pi plus 1 minus Pi by delta X. This again central differencing, but the grid size is delta X by 2. So this is also second order accurate, just that instead of 4 delta, this will be delta X by 2 whole square, but anyways, it's second order accurate. And then we have the diffusion term, which is straightforward as before. Del U del X square. So we are doing at this point. So you have to use this, and these 3 values. So that will give me ui plus half I plus 3 by 2 comma j minus 2 I plus half comma j plus ui minus half comma j by delta x square plus along y direction we'll be using again our central differencing. So these 3 points we should be using. So that should give me ui plus half j plus 1 minus 2 I plus half j plus ui plus half j minus 1 by delta y square. So the method is same. Like once you know this discretization, remaining everything else remains the same. The only difference is this additional quantity that we have here, vi plus half comma j. This is the only thing that we didn't have before, but everything else remains the same. So all we have to do now is estimate this from the predictor step. So we'll displace this with u tilde, use the previous values of pressure. So instead of n plus 1, we'll using n values, ideally it should be n plus 1, n plus 1. So use the previous values of pressure and then get u tilde. Once you have u tilde, then we have to do the continuity one. So for the correction step, we have to do the discretization of continuity equation. But this has to be done on cell centers. So on I comma j, so we'll have to do the discretization at this point. So at this point, del u del x is this minus, like we again use the central differencing. This will be ui plus half comma j minus ui minus half comma j by delta x plus del b del y. We can use these 2 points again central differencing. So vi j plus half minus vi j minus half by delta y equals to 0. So this along with the previous equations, the method is same as whatever we did before. You initialize somebody, get the correction, and from this we will estimate the the p prime. And once you get now instead of this one, this has only del square p del x square. Now we'll have plus additional term with respect to y square also. That will add another 2 pi prime. So this instead of 2 will have some, this omega will get changed, but other than that everything else remains the same. Here we have only u components. Now in 2D we'll have v components also. So we'll additionally have these 2 terms also getting added there. That would be the only difference. But other than that everything else remains the same. So if we were to see how to implement it, let's say in 2D, in the prediction step for u, so everything remains the same. So now we have the only term additional is this v average that was not there before, which is whatever I showed before, 1 by 4 of I minus 1, I minus 1 at jj plus 1 and I at j plus 1. So average of these velocities we will take, and from that we will calculate this is the del u del x term, which has u times del u del x. Maybe I should have written u times del u del x to be clear. This will be V times del u del y. So my advection term is u del u del x plus V del u del y. And these are the diffusion terms. And remaining u tilde is basically u plus delta t times pressure plus diffusion minus advection. So similarly for predicting V velocity, all we have to do is to change these terms accordingly. Previously we calculated V average. Now we will be calculating U average. So here we have U del V del x and we have V del V del y. This remains the same. Now for the pre-prime, we have this additional two terms coming into picture. So in the previous code, yeah. So for previous code, we just have del u del x term here coming in. But now we'll have for del u del x plus del u del y and all other terms also coming here. So we have divergence of x. This is different terms here. So we have del u del x, which is ui plus 1 minus ui by delta x, and similarly along del v del y, vij plus 1 and vij by delta y. So this will give me the divergence of u, and all we have to do is do the relaxation. Again, here we are assuming that the correction from the neighboring terms are 0. So we have to do another iteration so that this p prime will converge. So that iteration we will do inside the max step function. It basically calculates this p prime, and from there it corrects the velocities and use those as velocities to correct p, and then it repeats this thing till whatever tolerance we have specified is reached. Once the tolerance is reached, it will stop these iterations. So all these iterations are done within one time step. Like this, we have to do multiple time steps. That is where the next function comes in. So it does this depending on how many ever time steps you have. So here comes the current number that we discussed previously. So you have to calculate your CFL number and see whether it is, depending on the scheme, it is different. Here we are using central differencing, so it has to be less than 0.5 and so on. I think there are no questions in the implementation part. Just like 1D, the only additional term that we are adding here is this U average for the velocity, critical velocity, and V average for the Hall. These are the only additional terms. Remaining everything else is very similar to whatever is done in 1D form. We'll take some previous year assignment questions. If you have any questions, we can discuss them. Fine. Then we'll get started with these assignment problems. These are essentially for the exams. There I have seen some questions even in the discussion forum asking the format of exam and so on. The format will be MCQs, very similar to the assignment problems that you are solving and whatever we are discussing in these sessions. The questions will be very similar to this, like on the same level as what we are discussing now. Only these MCQs, either single option or multi option, but you have only MCQs, no descriptive questions. Okay. First one, the pressure in the UOP systems is solved from which type of equation in the marker and cell method? So how are we solving pressure? Is we are not directly solving it. We are essentially calculating Pn plus 1 as plus P prime, and in order to get P prime, we are solving an equation. Is something of this sort. Something of this sort, where this U tilde is basically my provisional velocity or whatever the predicted velocity is, and from this we are calculating P prime, and from this we are, so essentially what we are solving is this equation. This is the Poisson equation. And again, we are also simplifying this further, at least in the codes that I have shown. What I have done is I have essentially reduced this only into a single point form. So where del square p is kind of, I have neglected the neighboring inference. So this is kind of only local correction. It will not apply globally. So if you have to actually change the code, what we have to do here is, so let's take the 1D one first. So this is the P prime that I am calculating here. So I've calculated P prime roughly, and then using this P prime, I'll keep updating in my max step. So you compute some P prime. So this P prime will go into my correction velocity U, which will and then correct the pressure. So I'll have UV different now. So that will go into the next equation. So instead of doing like this, what we can almost reduce this number of iterations by essentially solving a Poisson equation directly here. So instead of just writing this, I can put a Gauss-Seidel solver here. Maybe I'll update it in the code next week. Once we discuss finite volume, then it will do better. Or you can try it yourselves also. Update with Gauss-Seidel solver. We already discussed how to do the Gauss-Seidel solver before, or Jacobi, whichever one you are convenient with. Jacobi, you can vectorize also, make it parallel and so on. You can try this. I'll upload this course. So you can try to implement Gauss-Seidel solver here and then get the final value of P prime, use it directly. That will reduce the number of iterations also. Which I have currently not done, but that can be done. Okay. Mass of following three types in CFT to their features. So the one that I started out with is the one that we discussed here is a static grid, and then we have something called collocated grid, which is basically storing all the values at the same grid points. So collocated grid is essentially I have these as my grid points, and I'll also have velocities also stored at the same point. This is collocated. Staggered is where I have cell centers and phase centers differently, or essentially velocity getting stored at different points, pressure getting stored at different points. This is my staggered. But as you can rightly see by now that whenever I'm using staggered, I'm essentially have to store two different ways of these grid points, and then I have to do some manipulation. There are other ways to do collocated also without facing the checkerboarding pattern. That I think we'll discuss that towards maybe next or next to next week once we enter finite volume. Okay, what are the characteristics of this? Is first pressure and velocity are stored at the same grid points. So this is basically collocated grid. Maintaining data structure is difficult. Which one will be difficult, staggered or collocated? Here I have to store two different grids, one cell centers, space centers, etc. Here all I have to store is just the cell centers. So this is a little simpler than this one. So little difficult in staggered. Pressure stored at cell center and velocity at places is staggered. Pressure velocity decoupling can lead to instability. So whenever we say decoupling, this is what we started out with initially. So decoupling essentially means that the odd and even vertices, the checkerboarding thing that we started out with. So that decoupling is happening when I'm storing both at the same points. This is qualitative. I don't think there are any questions in this. Okay. Which of the following statements about Mach algorithm in CFT are correct? Mach algorithm uses a staggered grid to avoid pressure velocity decoupling. Pressure is stored at cell centers or velocity components are stored at cell faces. These are all the terms that we discussed just now. The Mach algorithm computes the velocity at current time level before solving the pressure correction. Okay. So what about this statement? Does it compute the velocity at current time level before solving the pressure correction equation? And another point to note, we are solving an unsteady problem. So let's say our unsteady problem is 2D. This only we are restricting to 2D for now. So let's say I'll just write psi. The psi is P by rho. Incompressible flow, so rho is constant. How many boundary conditions do I need to solve this problem? So this is we have a time which is first order in time. So I need at least one initial condition. So I need to know u of x comma y at t equal to 0, v of x comma y at t equals to 0. It is second order in space for u comma v. So I need to know something at the boundaries. Similarly, I for all times. And what about pressure? It is first order in pressure. I need to know the pressure value at least at one boundary. Usually we'll fix that one free surface and we'll fix that pressure to be atmospheric, basically static pressure to be 0 and so on. So, but we need to know this at a boundary, either in Neumann or Dirichlet, whichever condition we have, but we need to know this. And we do not have any derivative of P with respect to time. In compressible flows, we have that, so we'll have to know the initial condition of pressure also. But here we do not need to know that specifically. We can just initialize it to 0 and then we can proceed it. But the problem is we need to know these two quantities. So do I also need to calculate, like do I have to specify the initial pressure to be able to proceed further? Like, so do I need to specify this P at T equals to 0 or not? Or will it influence the final result, the converged solution that we are going to get? Because your initial condition should affect how your solution marches in time and eventually your final solution. So here we are giving some initialization for u comma v, and again we are assuming that whatever initialization you are giving, we are using that and proceeding further. So if you see how we are proceeding, the time marching, like even before correcting, the correction, velocity correction is assuming that you already know the previous values of this. So you need to know the values of p comma u at initial time step, right? So if that is the case, do I have to know how exactly do I have to know these values? And do we know that in all the cases? Or maybe what happens if I give a wrong value for initial values of p comma u? What do you think will happen if I give a wrong value of pressure? So even the iteration process is starting with momentum equation. So we are not actually considering the continuity in the first step. We are using that in the next step. So for the first step, by using momentum, since we are not using continuity equation, we are assuming that the initial field that you are giving is divergence free, or essentially the continuity equation is satisfied by default. So if you give a field that is not divergent free, then you are going to have some problems with this. But coming to the pressure, even if the pressure is wrong, let's say, so eventually when you go to the pressure correction and we apply it such a way that it eventually result in a divergence free field of u, because we are using some pressure correction that is ensuring that the next velocity is divergence free. So if that is satisfied, then we do not have to worry about the initial condition of pressure that much. Compared to velocity, the initial condition of pressure is kind of relaxed. You do not need to know it accurately. Even if you do, initialize everything to be 0 or something, it will anyways get corrected from this equation later. Well, when we solve this equation, it will eventually get corrected. So we don't have to worry about p prime. We don't have to worry about p, but we need to make sure that the initial velocity that we are giving is the divergence p. And say for supposing for some problem, if you do not know whether your initial, like if you do not know the initial condition, then what we have to do is we have to run this pressure Poisson equation till sufficient number of iterations so that you will eventually reach a divergence field, and then use that field, and from there you do the time marching. So all the steps you have done until you reach the divergence free field are kind of not truly transient, or they do not really represent any physical thing. Only after that is when this thing becomes true. So you have to do some kind of steps before actually starting your time marching. That also means that you can always try. In the same code that I have shared, you can try that thing also. Okay, now coming to this one. So Mach algorithm computes velocity after solving the pressure correction equation. So before solving it does not compute anything. So you assume something. you get only u tilde, but un plus 1 is only calculated after solving for p prime. The convergence criteria for pressure correction in the Mach algorithm is that the divergence of the provisional velocity is 0. So this is what I was saying. We solve the pressure correction equation such that for the provisional velocity it will be 0. Ideally, it's not exactly 0. We'll just put some tolerance and we'll say that this is less than whatever tolerance we have. I'm just keeping it just to know that it won't be exactly equal to 0, but it will be within the tolerance, whatever tolerance you have specified, say 10 per minus 3, 10 per minus 2, whatever tolerance you specify. As long as it is within that tolerance, we'll stop the pressure correction equation. Okay. The pressure correction equation is obtained by satisfying continuity equation in which cells? So at cell center, continuity equation is always solved at cell centers because your velocities are kind of aligned perfectly so that you can do your ux plus vy thing easily. Just you can simply write it as both are at j, both are at I. You can simply write this things, but in order to write this, we are doing central differencing around the point I comma j. That will be my main side. So this for x momentum equation, and this for y momentum equation. Okay. Why do pressure and velocity get decoupled when using a collocated grid arrangement? Collocated grid arrangement is one where you store velocity and pressure at the same point. So by continuity, we'll have something like I plus 1 minus I minus 1, something like this going to 0. And the pressure equation will also have something like the same. So maybe you should have asked this another question, which I don't think it was raised before. Yes, the problem, as I said before here, was because I'm using pi plus 1 and pi minus 1. And instead of using central differencing, let's say if I use just the forward differencing or just the backward differencing, can this problem be solved? So what I meant is, let's say let's take the 1D equation as before, or even simpler, let's take steady state 1D equation. So I can write it as du dx equals to 0, and I have u du dx is, let's take density to be 1 and minus dp dx. Let's even neglect the diffusion equation. Let's just take this simple equation. When we are trying to solve this, we said that du dx equal to 0 will give me this equation, and when I have this, I'll write this as the momentum equation will become ui times ui plus 1 minus ui minus 1 by 2 delta x is minus pi plus 1 minus pi minus 1 by 2 delta x. So these are the two equations that I need to be solving for. So we'll have ui plus 1 equals to ui minus 1. So this will be equal to 0 and pi plus 1. So the solution for this set of equations is pi plus 1 is pi minus 1 and ui plus 1 is ui minus 1. So this means all the alternates will be equal and there is no relation between the neighboring cells. So that is the main problem for whatever we are calling as decoupling between pressure and velocity, or alternatively what we call the checkerboarding pattern. Only the alternate things will be equal, just like how a chessboard is black white get alternates. Here we have the alternate things being equal to each other. So now the question is, instead of using, let's say, a central difference scheme, if I replace this with let's say a forward differential scheme, where I'll write the same thing as can write just pi plus 1 instead of doing it at this ith point. Instead of doing central differencing, I'll just do the forward differencing. So I'll write it as pi plus 1 minus pi by delta x. I can do something like this. So this essentially will result because the first equation, this is from equation 1, this is from equation 2. So from first equation again I'll have ui plus 1 equals to ui minus 1, and if they are equal this will turn out to be 0, and from the second equation I can put pi plus 1 equals to pi. So here I have the neighboring connectivity, whatever I was getting previously, right? What is the problem with this thing? I can always do like this also, right? So even in odd cells, so for even cell it should be, let's say, u2 u3 minus u1, and for an odd cell this would be, so eventually p2 will be equal to p3, p3 equals to p4, and so on. So all the cells will be linked to each other and I'll be able to solve this thing. So what is the problem with this approach? We are kind of compromising on the order of accuracy here. So if you use the central differencing, we were getting second order accurate. If you're using a backward or forward differencing, we'll end up having only a first order accurate system. But for velocity, we are using a second order accurate one, which is kind of not that useful. So we can do a second order accurate system directly. With the staggered gate, we were able to get second order accurate system directly. Anyways, coming back, so why are these getting decoupled? Is pressure is not included? No, pressure is included in the momentum equations. Pressure gradient is ignored in the numerical scheme. No, we are actually calculating the pressure gradient also. The pressure gradient at the cell center is calculated using neighboring pressures, not the pressure of the cell itself. This was the main reason. Pressure and velocity are stored at the same length, not at corners or something else. Okay. Which scheme is used for spatial discretization in the MAC algorithm? As you can see, everywhere what we were doing is for the cell centers or the other way around. In both of these cases, what we are doing is this is delta x by 2, delta x by 2, delta x by 2, delta x by 2. We are using only central differencing scheme. So, for example, del p del x, we have to write at this cell point. So, sorry, del p del x will be del at the phase center. We will have the value at this point minus this point, I plus 1, this is I plus 1. So, we are writing delta x here, but this is actually a central differencing scheme, which is second order accurate. The same for velocity also. So, for velocity, you will be solving, so let's say in the continuity equation, you are taking del u del x. In continuity for del u del x, you are doing at the cell point at this point. So, this is my I, so this is my I plus half, and this is my I minus half. So, I'll have ui plus half minus ui minus half by delta x. So, this is also central difference only. And in the momentum equation, we are doing a slightly different thing where we are discretizing at this point. For example, if I want to calculate del u del x here, I could have done ui plus 1 again minus ui by delta x, but again I am, instead of this, what we are doing is we are expanding this a little. We have I plus 3 by 2 and we have I minus half. So, so essentially what we are doing is again a central differencing, but on the bigger coordinates. So on the bigger stencil, we are doing central difference for these nodes, and that will give me ui plus 3 by 2 minus ui minus half by 2 delta x, which is also central differencing. You can also do this here. So ui plus 1, you can do an average of these two and say that is basically my. So you can write ui plus half as ui plus 3 by 2 plus ui plus half by 2. And similarly for ui, you can write as the average of the other two quantities. Is ui plus half plus ui minus half by 2. That would also give you the same equation. But the key point here is any differentiation or any spatial discretization that we are using in the Mach algorithm, all of them, for pressure gradient or velocity gradients, whatever we are using, are central differencing. Why is under relaxation factor used in the Mach algorithm? To correct velocity, to accelerate calculation of pressure correction, decelerate the calculation of pressure correction. Under relaxation factor is not used in the Mach algorithm. So where are we using this factor? If you recollect, so we have a pressure Poisson equation that we are trying to solve. Is del square p prime is minus rho delta x by delta t times del dot t theta. So this is my provisional velocity. So this equation is what we are trying to solve using Gauss-Seidel method. If you are using a Gauss-Seidel method inside the Mach algorithm, this is where we will use some kind of relaxation factor. Whether it is under or over relaxation is something that you have to look into. What we actually do is when you use a Gauss-Seidel for this kind of pressure Poisson solver, they usually become very slow. So what we try to do is we kind of use the higher value over relaxation to kind of accelerate the calculation of pressure. So what this question says is under relaxation, but it's actually over relaxation is what we will be using. So it is not actually used in that. Okay. In Mach algorithm, the pressure correction in the neighboring cells are assumed as 0, which we are doing now. The pressure correction equation obtained by satisfying the continuity equation is just as I told, it's a Poisson equation. Del square p prime is rho times delta t, rho by delta t times del dot q. Okay, there has to be minus somewhere. There is no minus because that gets cancelled. Okay. This equation. This is the last question. The equation for the updated v velocity in the Mach algorithm is obtained as. So for any velocity, the updated equation can be written as, to recollect the original term, so we have v n plus 1 at I comma j plus half is v tilde, whatever you're obtaining at I comma j plus half, minus delta t by rho delta x. I don't think we have a delta x also. This is along y direction, so this is d delta y times del p del y, where del p del y will have, if my cells are like this along the vertical direction, so del p del y will be I j plus half. Sorry, we are doing at this point j plus 1 here. So this will be p I j plus 1 minus p prime I j by delta y, which I already have. So this is the equation that we'll be solving. So essentially what this is we denote this as the p point, which will be my north point. So Vij plus half will be Vp bar. This is the corrected velocity, this is the provisional velocity that we are having, minus delta t by rho delta y times Pn prime minus Pp prime. This is how we obtain the velocity at the next time step. Okay. Now we have already looked into coding problems. So let's take one simple problem where 1D channel flow. So where you have a grid and let's say we specify velocity v equal to so and so. And then here let's say we say du dx is 0. And we need to solve this problem. So now we'll see how we can actually solve this. And one problem here you can see is what will be my initial velocity throughout, what should be my u of x equal to 0. If for suppose I define it to be 0, let's start from here. What is the problem with this? If I define it to be 0, then I have du dx is not equal to 0 at inlet, which essentially means if I define something like this is not a divergence is not equal to 0. This is not actually satisfied. So let's see what happens if I do such an initialization. So let's take case 1, which is the first problem here. So what we are doing is we are discretizing with n equal to 100, dx is 0.1, dt is 0.01, and I am defining p to be 0 throughout and u also to be 0 throughout, which as we know is not correct. And the boundary conditions are at first cell u is 1 and for the last cell du dx is 0, which is essentially u n equals to n minus 1. Now for the pressure, we apply Neumann condition at the inlet and Dirichlet condition at the outlet. First, what we are doing is we are taking this thing, we are imposing the boundary condition on that so that the initial field satisfies boundary conditions, but we are not checking whether this is satisfying the continuity equation or not, which is something that we will not do in the Mach algorithm, which we are assuming by default. And then we'll run this thing and see what happens. It gives some result, but the thing is it does not have any kind of thing. So you can see where it reached to. It eventually reached a point where u is kind of constant throughout the domain, which we already know the solution for this particular problem is. But now let's do something else. Let's see how many iterations it took to converge. Huh. This is what I was trying to show you. So you can see initially, most of the initial iterations are they did not actually converge. The residual is actually greater than 1. But as you can see, as the time progresses, all these time steps where it reduced, and only after a given point, here is when it kind of reduced below 10 power minus 3 or whatever threshold I have set. So up until this point, the time, even though we are saying we are marching in time, all these steps are not actually physical time steps. So what is happening there? It is the solver is trying to find a solution where, and that is done in a like it is not it is like a pseudo solution. It's not actually a real solution. All these steps it is actually not a divergence free, but we can also do something else now. So instead of zeros, let's say I start with a divergence free field because u is 1 at the inlet. I'll just define it to be constant throughout. So instead of 0, I'll just put equals to 1 or whatever the velocity that I'm keeping here. So this is 1, so I'll just keep 1 everywhere. And now let us see what happens if I run this. Yeah, now you can see the solution. You can see it converge instantly in almost all the cases. Again, I kind of used some under relaxation here in the previous case just to get some solution, single solution, but you can see the velocity is 1 everywhere, which is what we already know, and pressure is kind of 0 constant everywhere. Velocity is constant, so there is no pressure gradient. So this is the trivial solution that we get accurately, which was not the case when I started out with a velocity field that is not divergence free. Now I can also do something here where I can alter this thing. So I kept 0.6 here. So by 2, so this should have, and let's say I make it 1.2 or something and see what happens. So what are we doing now is we are trying to increase the relaxation factor. This should not affect that much, but let's try this out also. Yeah, it's the same, it doesn't change, but you will see the problem in the other case. So what happened is we are doing an over relaxation. So when we are doing over relaxation, we are trying to accelerate the convergence, but because the solution converges in 2 iterations, we did not see anything here. But if I were to define a field which is not divergence free initially, so instead of giving a divergence, if I gave a field which has kind of the star gradient initially, then maybe I'll reduce the number of iterations to 100 or something so that we don't have to waste time there. If I reduce this, then what we expect is, because now there are some oscillations at the inlet. So what we are expecting now is when I give 0, there will be a sudden gradient in velocity at this particular initial stage at the inlet. And what that will happen is if I'm using an over relaxation, so those oscillations or those amplitudes will keep growing in time. And that should actually kind of give me a divergence. Yeah, you can see the divergence here. You can see that it will never reach a solution at all. So this is why we the first field, the initial guess or not the guess, the initial u at t equal to 0 should be a divergence free field. So this is the first step that we need to make sure. So as long as this is divergence free, then we'll have initial solution. But in all problems, it will be very difficult to get a divergence free solution always, because sometimes finding that itself is actually a problem. So what we will do is initially run through some iterations so that you will actually eventually get that pseudo kind of thing and reach a point where you have a divergence free field, and from there you start your transient solution. Let's take another example. Let's say this example is clear. Let's take another example where now what we did here is we fixed the velocity here. Let's take the same problem where instead of fixing the velocity, I'll fix the pressure. So I'll say pressure here is say 1 and pressure here is say 0, something like this, and see how the velocity will change. So everything else remains the same. All we're doing is I'm making pressure equal to 0. If, so my pressure condition I'm keeping at 1 is 0.1 and at 0 as 0. At the other end as 0. U I'm keeping 0, 0 everywhere. And you can keep no slip instead of no slip. You can try it something else also, outlook condition or whatever, but no slip is the easiest one to implement, so I've just taken that. So now what we are trying to do is same as before. So if I just run this, so what would you expect? What we are trying to solve now is let's say we run it till steady state. So I'm taking mu equals to 1 and so on. Mu is 1 is very high for this particular problem. So what we would expect now from this with the initial with these boundary conditions and u equals to 0 at left and right. Yeah, you can see the problem here. So it did not convert. So what can we do now? So when things like this happen, what are we supposed to do? So whenever you see something is kind of diverging, all we have to do is change our relaxation factor so that it will eventually reach a solution. In this case, we'll reduce this to say 0.6 or something. Then it will kind of reach a solution. So, yeah, you'll get that whatever parabolic velocity profile that we expect for this one problem. This is actually not a 2D channel flow. This is just to kind of illustrate that you can actually do this with MATLAB. Nothing more fancy. And then the last case, which we already did in the last week, is the lid driven cavity problem. So you have all this as walls. And then we have this uniform velocity u imposed on the top surface. So how do we implement this? That is my last case. So the boundary conditions are all the walls you have 0, 0, 0. At the top end you have u lit. Velocity everywhere it is 0 because the top wall is impenetrable or impermeable. So you have the vertical velocity to be 0 everywhere. For pressure, it is del P del N equals to 0, 0 gradient. For all the walls we have along the wall the pressure gradient has to be 0. So it should be equal to whatever is the previous step. So these are the boundary conditions, and then everything else remains the same. Let me just run this. So the solver is already shown before. The only thing is you have to apply the correct boundary conditions and then run the solver. Yeah, here you can see the initial field, initial velocity that I'm assuming again here is zeros, which is again a problem because no, in this particular problem we do not have a problem as such. So here what should be my velocity field? So if I've assumed u equals to 0 and v equal to 0 throughout, so I have del u del x plus del v del y if you were to take. If velocity u is 0 everywhere, at this particular grid point if I take, then del u del x is 0 and we have del v del y equal to 0. So we do not have that problem here. So we can start with 0 everywhere. And okay, instead of pressure, I should see the velocity r. This is what we have already seen before, that symmetric thing that we saw before. We solve this using what is the stream function formulation also, and we can solve this using Mach algorithm also. That is what we just did. You can see how symmetric it is. But if I increase the Reynolds number a little bit more, then the problem comes. Here, this is for a very low Reynolds number. I think I've taken Reynolds number of around 1 or something. You can check that in the diffusion term. Yeah. So diffusion uses nu equals to 1. So this is basically for a Reynolds number of 1. If you increase the Reynolds number, you will see some vortices forming here and so on. But the idea is clear, I guess. I don't think there are any questions in the implementation. Yeah, so these are the questions I have for this week. To summarize, we started out with saying that instead of vorticity state function formulation, the problems that we had were defining the boundary conditions is always difficult because we do not always have boundary conditions in terms of vorticity or stream function. We usually have them in terms of the primitive variables, velocities and pressures. So how do we solve? So we have to write our equations in terms of these primitive variables and then solve them also in these variables. That is where Mach algorithm comes. But the main problem with respect to finite difference in Mach, with the finite difference is if I store everything in the same grid point, then I'm having this problem of checkerboarding where the gradients at a given cell point are depending only on the neighboring cell points without actually depending on the current value. So the strategy to overcome this is I'll solve the continuity and momentum equation on different grids. The continuity will be solved on the cell grids and momentum equation will be solved on the phase centers. So that way what we are doing is we are kind of enforcing the coupling between pressure and velocity, and that is called a statute approach. And then we expanded this in the Mach algorithm where we have to solve the momentum equation where we have two unknowns, the pressure and velocity, both of being n plus 1 terms. So why did we write n plus 1 here? I could have written n and go ahead, but then the problem is for incompressible flows, we do not have a del P del T term. We cannot do time marching in terms of pressure directly. So I have to use n plus 1 here. If it were a compressible flow, then in the continuity equation, I'll have a del P del T term, which I could use to march in time for pressure, which I do not have for incompressible flow cases. That is the main challenge. So what we are doing now instead is we are doing some prediction and correction step, where in the predictor we will assume we will get a provisional velocity by assuming the previous pressure as a current pressure. So this is obviously not the velocity that we are looking for. So we need to find the velocity we are looking for, and for that we will use a continuity equation. And how do we use that? Is we substitute this, we use something called pressure correction, which will tell us how much to change this pressure. And we have to increase that in such a way so as to satisfy the continuity equation. And that gives us the next equation, this pressure Poisson equation, which we have to solve. In Mach, we kind of simplified it saying that the neighboring effect is neglected and you can directly get Pi prime. And then what we are doing now is instead of solving the pressure Poisson equation, we are iterating only in this direction. What this iteration does is eventually you reach a solution for you eventually reach a solution for Pi prime. Once I have Pi prime, I can compute Pn plus 1. And once I have Pn plus 1, even without this, I can directly compute Pn plus 1 in terms of P prime, which I already have before. So this from P prime, I can get this equation. I think I have written here. Once I have P prime, I can substitute with the corresponding U tilde and get to Un plus 1. The same extension is for 2D discretization also, but in 2D what we are initially will have is a V term coming here, which we are not storing at the corresponding cell point. So what we have to do is an average of all the neighboring points. So if you need velocity at this particular point, we are doing average of all the neighboring points. That will give me the solution. And then we discuss some previous tutorial problems and some coding examples. Yeah. Have any questions? Yeah. Thank you for joining. If you have questions, we'll meet next week same time. Next week we'll start discussing finite volume method, which is something that is widely used nowadays. We'll see what is the problem with finite difference and how that exactly has been kind of solved using finite volume and why that is most prevalent nowadays compared to finite difference. Thank you for joining.